Hey developers, this is Marco Arruda. In this video I'm gonna show some basic example about the TF2, which is the transformation library for ROS2 to handle transformation frames in ROS. So as usual I'm gonna use ROS in the construct platform. If you don't have an account yet, remember you can start using just for free. Create your account here in the sign up button, and I'm gonna use my regular account and I'm gonna open this ROS2 concepts projects. This is a ROS2 Foxy distro project, so just press the run button and wait a few seconds until you get the environment ready. In the meantime, let me show the official docs of the ROS2 TF2. So the motivation of having this library to handle transformation frames for us is that things can become very complex in robotics, since a single robot can have multiple joints and links, and while working with robots you may need, for example, to transform the end effector position to the world frame to grasp some object, for example, or just to point the camera to a specific place. And having transformation frames is very helpful for us developers. Okay, great. So getting back to the workspace, I'm gonna have some shells open here. Okay, almost there. My files are being downloaded. Let me click here in the web shell in the meantime and also open the IDE. And I'm gonna start by copying some of the examples that I have prepared. And let's start by creating a new package. Close the notebook, I won't need it. Let's keep the ID aside, for instance. And finally in the shell, so I have created this project before. If you are creating your own just right now, make sure you have in the bashrc file this source command here. So I basically placed the source command because I want to have ROS2 set up whenever I start a new shell. Okay, otherwise we will have ROS1 environment configured. Yeah, so go to the ROS2 workspace inside the source folder. Then I'm gonna create a new package. I'm gonna call it TF2 examples, and I'm using the build type mn Python, so I'm gonna use Python to work here. There it is. And now inside the IDE we'll have the source folder and TF2 examples, the package I have just created. And as my entry point, I have the my node known for the TF2 underscore examples file. And this is the file that we can find just right here. And I also want to have a launch file. So in order to have it, I need to import some libraries in the setup file. So just put it here and configure the compiler to consider and to share the launch files of our packages into the installation folder. Yeah, great. And almost there. Then in the package XML file, we also need to specify that will depend on launch and launch ROS. And finally, we need to install some of the dependencies. So just right here in the tutorials, you're gonna see that we need to install. Let me put it here. We need to install some libraries. They are quite wide, so it's quite fast. So just sudo apt update. Install the necessary libraries. Yeah. In the meantime, go to the my node file, and we're going to start from one basic example of the official documentation. This is basically starting a new node, frame publisher, and this frame publisher is publishing two reference frames, one for the world, which is supposed to be static. Actually it is static, and its child is the turtle. So in this case, we're gonna have the turtle scene simulation running. So turtle 1 is the child of this reference frame. And I am considering here that the turtle is spawned at the center of the world, and I'm considering this as 0. So whenever we start the simulation, we'll understand why I'm using those values here. So basically, the turtle scene world doesn't consider the center of the world as number 0, and in this case I am transforming. So let's show in practice how it does. And we need to install one more thing for Python, the transforms 3D. So we just had the other libraries installed. Install this one as well. Now that we have it, go to the root folder of the workspace, call compute. So we are compiling this package. And we're gonna, well, actually we need a launch file. So I'm gonna create a folder here, launch. And inside this folder, let me just copy and paste what I have here. I'm gonna call TF2 examples example.launch.py. I'm using a launch file because despite I have a command already to launch my node, I want also to restart the turtle scene simulation whenever I start the TF broadcaster here. So yeah, we have the launch file with the turtle scene and also the turtle TF example. This is the name of the package. Actually, the name of the package is TF2 examples, so I need to change it here. And the executable is my node. This is correct. So recompile. And even though I'm working with Python, yes, in ROS2 I need to recompile my package because it is kind of copying all those files here, the scripts and launch files, to the common share folder of the workspace. Finally, source the installation folder, setup bash, and we can try ROS2 launch. The name of the package is TF2 examples, and the name of the launch file is turtle TF2 example. Press enter. Okay, I may have forgotten something. Let's see, what is the issue? Turtle TF2 example not found. Turtle TF2. Where do I have it? Okay, so the name of the package is TF2 examples. Let me remove the install, build, and log folders and recompile. There may be some trash from the last time I working in workspace. Okay, the name of the launch file is not turtle TF2 example. It is actually just tf2 example.launch.py. Yeah, so there it is. Now we have the turtle scene being spawned, and also a second node for the broadcaster, which is this my node executable here. Let me open in the meantime a second shell and also open the graphical tool so we can visualize the turtle scene. Many things should be open at the same time. Yeah, so ROS2 node list, and we have the broadcaster and also the simulation. And here we have the turtle scene simulation. It's already working. I want to have ROS2 running so we can visualize the frames. let me create a new shell in the meantime, and then we can start moving the robot. So Arvis is getting ready, and here we can run ROS2, run turtle sim, and then turtle teleop key. So yeah, there it is. We have here in Arvis. I'm gonna put this. I'm gonna collapse this menu. Put Arvis to the right side, and we can have the simulation here to the upper corner. There it is. Our fixed frame is the world, and then we can show the TFs that we have there. So just press enter TF, and what do we have here? So it's showing just a single frame, at least it appears so, but if you check the tree we have world and the turtle. And yeah, let's run the teleop. What does it happen there? So I'm gonna control the turtle, I'm gonna rotate it and send forward. Okay, great, there it is. So as you can see, we have a reference frame for the world, and this is actually the center of the world. That's why I'm using the calculation there, because the position of the turtle actually, so let me put it back to the original position, so it's just in the center of the world. And if we check here in another terminal, you can see ROS2 topic list. We have the position of the robot like this, so ROS2 echo turtle1 pose. Actually, it's ROS2 topic echo. And the position of the robot is 5.54. This is because this is the value that represents the center of the world. So this is why I am compensating here in the my node file. Okay, so I am decreasing exactly this value, which is 11.08 divided by 2. So this is the center of the world, and this is how I am compensating. And this way, the TF, the frame of the robot, is considered as 0 when the robot is in the center of the simulator. Okay. So yeah, that's it. Basically, this is how we can have a transformation frame. We have created one for that represents the relation between the turtle and the world. So let's now go one step further and create a new reference frame. Let's say, for example, that we have a drone following the turtle, which would be very interesting actually. And in this case, we have only the relation between the drone, because the drone, let's say, was configured to follow the turtle, and it should be always in the back of the turtle, and some with a fixed distance to the turtle. So in this case, I need to create another transformation frame, and it is somehow related to the turtle. Let's put it here, the relation between the turtle and the drone. And here I'm gonna use as the header stamp the same time that we have been using for the relation between the turtle and the world. This is because we're gonna use the same clock, and in this TF library we are tracking the position of frames regarding to each other with a based on time. Okay, so it's tracking with the time, so time is passing, and we are still tracking and showing real time the position between those references. And here the frame ID would be the name of the turtle, and the child is the drone itself. Okay, and what is the relation between those two? I'm gonna put it here some fixed relation, and for example, we can set up like, okay, so actually I think it's better if I put this frame here, and then the position of the transformation will be, so the drone will always be ½ meter behind the turtle, and also 1 meter higher, so in height it will be of course flying, and let's say the camera is pointing downwards to the turtle, so that's why we need to be ½ meter behind. And finally, for the quaternion, I won't do anything complex here, so it will always pointing to the direction of the turtle. So we have the transformation set up, and whenever we receive a position from the turtle, we're gonna also publish the position, the relation of position between the drone and the turtle. And yeah, I think that's it. So let's recompile the node. I need to kill it. The launch file. Build it again. Great, it's quite fast. Relaunch. And as you can see, we have one more frame here. So the turtle started at the center of the world, and just behind the turtle we have a drone. So we configure the position of the drone half meter behind the turtle. So I think it's makes a lot of sense, the situation that we can see here. So 1 meter higher in relation to the floor, and half meter behind the turtle. And then let's move the turtle again using the teleop. For example, I'm gonna rotate it. Okay, so what is the button I need to rotate? I think R. Yes, there it is. And as you can see, the drone is rotating with the turtle. So if I rotate it back again, it's always following the turtle. And if I go forward, the drone is also following like this. And yeah, basically that's it. So let's check now the final advantage of having the transformation frame, because for us it's quite simple and it's quite obvious, because we have the position of the turtle in relation to the world, and actually we have this position here, this original position. But let's say we want to know the position of the reference frames that we have created, which is the turtle and the world. So in this case, it should be something similar to 2 meters in the Y position, for example, because we're not considering this reference frame anymore. Remember, we have compensated some values here, and there is a command that we can use, which is okay. Let me check here. We can use the ROS2, run TF2 ROS. This is the TF2 ROS package, and it provides a lot of executables. So one of them is the TF2 echo, and then it's like echoing the pose of the robot from the simulator topic. But in this case, we want to know the position regarding to the transformation frame. So we need to tell, we want to know the position of the in respect to the world, and the position of the turtle one. So it goes like this. And then we have translation in the x-axis, almost 0, almost equals to 0, as you can see here. And in the y-axis we have more or less 2 meters, okay? And since we are dealing with a ground robot, so position in z-axis will always be equals to 0. And yeah, very interesting. So now if we check the position of the drone in respect to the turtle, we should have always the same value, because the drone was configured to be always half meter behind the turtle and 1 meter higher in relation to the ground, and as a consequence 1 meter in relation to the turtle as well. Okay, but now we want to have something more complex, which is we want to know the position of the drone in respect to the world, because we never set up this relation before, and actually this is something that needs to be calculated, since the drone is moving and keeping a constant position in respect to the turtle, but the turtle position in respect to the world is not constant, because we are moving it. So at this moment we have, for example, the drone, in which it makes a lot of sense. As you can see, the displacement to the x-axis is almost 0, so very is the same value actually like the turtle. And in the y-axis we have half meter behind the turtle, and it's constant, the value on the z-axis. And then if we move the turtle again, I'm gonna do a rotation, for example, and go here, then we're gonna have a different position. So 3 meters here, almost 1 meter in the x-axis. And yeah, so this is the advantage of using TF2. This is how you can configure a broadcaster and also create this relation and compensate some values. So as you can see, you can configure TF2 transform to show the values the best way for your application. So yeah, that's it for today. Don't forget, if you like this kind of video, leave a like, leave a comment, please let us know your opinion about the content we are posting, and don't forget to subscribe to our channel and press the bell. Okay, great, so see you in the next video. Bye.